Everyone, another day, another LeetCode problem. So today we're going to be looking at 207, that's course schedule. And the same logic will also go for course schedule too with like a one-line difference. So we're going to be looking at this in both the DFS and the BFS, the Kahn's algorithm kind of approach. So yeah, let's just go ahead with that over here. All right, so what the problem tells us is that we're given a total of number of courses. So this value of the total number of courses is also given to us. And then we're given a prerequisites kind of list over here, which we see, and then we have the number of courses. So what exactly they're saying is prerequisite has like A and B, where it means that to complete the course A, you have to have taken the prerequisite course of B. So yeah, this is the same thing I've written over here. So yeah, these are the things that are given to us. And the goal of it is we have to tell them if it's possible for us to take all of the courses. And the translation of this is actually saying, so can we complete all these courses without there being like a kind of loop or a dependence? So basically, we have to tell that there are no cycles, okay? So if there are no cycles and we can complete everything, then yes, we can take all of the courses. So that's basically what we're trying to find out over here. So let's look at an example. So here, these are the same examples that are given on LeetCode. So the number of courses here are 2. So we have a course 0, and then we have a course 1. So they're saying to take course 1, you should have taken course 0. So yeah, 0 is the prerequisite to take 1. And then here again, we're given 2 courses. So we have 0 and 1. And to take the course 1, we should have taken the course 0. And to take the course 0, we should have also taken the course 1. So we see that there is a loop. So this would return false because it's not possible to take all the courses. And this would have returned a true because it is possible. All right, so let's look at the DFS approach first. So basically what we do is we just go and check if there are no cycles, right? So let's see how we're going to do that, and then we'll go ahead with the Kahn's algorithm approach for this. So one thing, initially, when we're given a graph like this, we want to map the nodes out such that we have a node and then we have its neighbors. So in this condition, we're given the course and its prerequisite, right? So I am going to be mapping course to all of its prerequisites. We can take like a default dictionary of lists over here. So 0 has nothing, so that's like this. And then 1 has a prerequisite, which is 0. And then we see 2 over here. So 2 has a prerequisite, which is 5. So it has a prerequisite of 5, and then it has a prerequisite of 4. We see 3 has a prerequisite of 2, and we see 4 has no prerequisite. So that's there, and we see to take 5, we don't need to take anything else, so that's empty again. And to take 6, we have to have taken 5. Yeah, I think that's correct. To take 4, nothing. 5, nothing. Okay, 6. All right, so here's what we're gonna do. We see that there are actually 2 components over here. So we're gonna start a DFS from each of our components if it's not visited. So we wanna do one thing. We wanna check if there are cycles, right? So here is the process that we're gonna follow. We're gonna have something like a set, which holds the nodes that we have covered in our current component, which is going to be cycle, and then we have something which is visited, which is going to be another set. So once we know that something can successfully be traversed and like completed, we're going to add that to visited. But until then, it's going to lie in our cycle. And once we know that we can complete it, we're going to remove it from the cycle. So let's just check that out. And I think it'll be easier. So I'm going to start from 0 over here. Okay, once I start from 0, I'm going to look at all the prerequisites that were required to take 0. So in this case, 0 has no prerequisite. So I know that 0 can definitely be completed. So right now 0 is added to my cycle. So I went to check the prerequisites, but I saw that there were none. So I know that 0 can be completed. I will add 0 to my visited set. And now I'm going to go to the next node, which will be in the range of number of courses. So after 0, 1 comes. All right, so I go to 1. I'm going to add 1 to the cycle. And then I'm going to look at the prerequisites of 1. And the prerequisite of 1 is 0. And 0 is in visited. And the meaning of visited is something that can successfully be completed. So if it's in visited, then I know that it's possible to complete. So I know that 1 is also possible to complete now since there are no dependencies. I'm also going to add, so this was 0 actually. I'm also going to add 1 and say it's possible to complete it. Now 0, 1, I'm going to go to 2. So once I come to 2 over here, I add 2 to my cycle. Then I look at the prerequisites of 2. So the prerequisite of 2 is 5 over here. And then I check for the prerequisites of 5. It has nothing. So I add 5 to the cycle as well. But I see that the 5 does not require anything else. And since it can successfully be completed, I add 5 to visited. And I remove 5 from the cycle. Then I come back to 2. And because 2's prerequisite is also capable of being completed, I add 2 over here. And then I look at 3. So the prerequisite of 3 is 2, which is successfully possible to complete. So 3, and then 3 is removed, and that's also added to visited. Then I look at 4, and I add 4 to the cycle, but 4 does not have any prerequisites. So by default, it does. It is capable of being completed. Then I go to 5, which has already been completed, so I don't need to traverse that. Then I go to 6 and add 6 to the cycle. Then I see the prerequisite of 6 is 5, which is possible to be completed. So I add 6 here and I remove it from that. So this is our actual, it's our visited set, and we can see that the size of visited is also equal to the number of courses that we have. So it's 7. And number of courses is also 7. So I can tell that there are no cycles and it's possible to complete it. Now, let's check the condition that, let's say, 6 was actually connected back to 5. Now, what would have happened was, when I came to 2, I would have gone to its prerequisite, which would have been 5. And at that point, my cycle would have had 2 in it. And then I would go to 5, so the cycle would be added with 5. And then I would look at the prerequisite of 5, which would be 6, and I would add 6. And then I would look at the prerequisite of 6, which is 5, and that is where I would have seen. But 5 is already part of the cycle. So if it's already part of the cycle, that means I'm going in a loop. That's where cycle actually comes into play. And then I would have returned a false, which would have told me that there is a cycle present. And once I return false, I immediately return false back. So that gives the answer to our question of whether or not we can complete stuff. So false means no, we cannot, and there were cycles present. So yeah, this is the way to do it. And one more thing is that, yeah, here we've used visited. Another step that we could have followed would have been for course schedule 2, because in course schedule 2, we're actually looking for the order in which courses have to be completed. So if I had just kept a list here, which was order, and because I'm going from course to prerequisite, so I know that DFS takes it to the depth of it, right? So I'm going course to prerequisite to the prerequisite of that. So I know that at the end point of where my DFS would have ended, that is where I would have had my initial origin course, which would have been the prerequisite of everything, and then the next one and the next one, right? So when I go to the depths of that, so basically at this point where I'm removing from cycle and I'm removing from visited, that's where I would go on adding it to the course, the course order list. So yeah, we would have an order list over there. So let's remember this step. I'm going to code it up later so we can see that. But yeah, this minor change of just storing values is what would have helped us to solve course schedule 2 as well. So let's look at the time complexity of this. So I see that I'm going to a number of nodes. So I'm checking all of the nodes, and for those I'm checking the edges as well. So it's V plus E vertices, and then edges, and then space. So I'm using a visited set, a cycle set, so it's O plus V, and then 2 times this because I'm also using a stack space here, so it's a recursive stack. But yeah, leaving constants, it's of v. Okay, so now let's look at the way to solve this with Kahn's algorithm. So as we had seen in Kahn's algorithm, what we do is actually we have an in-degree mapping over here for each node. So let's just look at that. So there's no 0 here. In degree of 1 is, so the number of courses given here. So let's say number of courses is 3, 4, it's actually 5. Let's see that. So in degree of 1 is 0. In degree of 2, as I can see, is 1. And then in degree of 3 is, so there's 1 here and then there's 1 here, so it's 2. In degree of 4 is 1, and in degree of 5 is also equal to 1. Okay. So we start off with the queue, right? And initially our queue would have the value of node 1 because its in degree count is 1. So let's also keep like an order list over here. So in this case, what we do is initially we start adding those nodes because anything with an in degree 0 means it's possible to complete, right? So here 1 would be added. And then I see once I remove the node 1, it affects the node 2. So node 2's in degree count becomes 0, right? Then I add 2 over here. And once I pop out 2, I see that it affects the in degree count of 3, 4, and 5. So 3 goes to 1 in degree, 4 goes to 0, and 5 also goes to 0. And 2 is added here to the order. So now we have 4 and 5. So let's go ahead, let's add 4 and 5. And so yeah, we'll pop out 4. So once I pop out 4, it doesn't affect anything. It can be completed. And once I remove 5, so 5 is also completed now because it already had 0 and was popped out. So 5 affects the course 3, and 3's in degree becomes, it also becomes 0 at this point. So 3 is added over here. And once we pop out 3, we can add it over here, and basically it doesn't have any courses dependent on it. So this becomes our output, and this is the order in which we have to take courses as well. And if we see the size of this is equal to 5, which is also equal to number of courses, which is 5. So we can tell that there are no cycles. So yeah, that's how we solve this using Kahn's algorithm. Now I'm going to go ahead and code up both of these solutions, the DFS approach, as well as the Kahn's algorithm approach. So I think it'll be easier to understand. So what did we talk about in DFS, right? So one thing I mentioned was that, sorry. So I'm going to have a visited set over here, which is for successfully completed or successfully capable of being visited. Then we're going to have cycle set over here. Okay, which is going to maintain our current cycle. Then what else did we want? So yeah, I'm just going to write out the solution for where we actually store the values, because I'll copy paste this to course schedule 2 and we can try that again over there. So let's say this is order, and then we want to have a mapping, right? So let's just consider an adjacency list over here. So let's keep that as a default dictionary of list. So first thing was that we traversed to kind of map everything to its prerequisites. So let's do for course and prerequisite and prerequisites. I'm going to do adjacency list of course, and I'm going to append this prerequisite. All right. So then we wanted to have a DFS. So let's just say can finish or something. Okay. Can finish. Can finish at this course. All right, so we'll fill that up. But before that, what we were doing is we were starting from each node to kind of see if we could finish it, right? So I'm going to do for course in range of number of courses. And immediately, if I cannot finish it, then if I can finish of course, then I want to go ahead and return false. But if everything was completed, then we're going to go ahead and return a true. All right. So we need to make sure that this returns a true or a false. And we'll just fill this up now. So what I said was, if this course is in our cycle, what we're going to do is return a false because we know we can't complete it. But if course is in visited, I mean, it can successfully be completed, then we don't want to traverse it again unnecessarily. We can just return true because we know it's possible. Okay, so the first thing is every time a node comes, we don't know if this node can successfully be completed, but we know that it's a part of our current cycle. So we have to do cycle dot add if this course, all right? And then we're gonna go into the prerequisites of that course. So we're gonna go to for neighbor and adjacency list of this course, and we're gonna start checking if that can be finished. All right, so if we cannot finish it, that's where we want to return false, right? So if we cannot finish this neighbor, then we want to go ahead and return false. But if we can finish it, then we want to kind of mark this and say that it's possible to complete this node, but that doesn't mean everything is possible, right? So we don't want to return true immediately, but we do want to remove it from our cycle. So we remove course from the cycle, and then we add it to visited, so it's successfully possible to visit it. And we're gonna do order dot append this course. Like I mentioned, so since we go from course to prerequisites, so the end of our DFS will actually have the initial prerequisite of everything. So yeah, and then after that we can return a true, because I believe if I don't return true here, it's gonna return a false. So we don't want to mess that up. But yeah, let's see. So we start from here. We're gonna go check if it's in our cycle, then we return false. If it's in visited, we return true. We add it to the cycle, then we traverse its prerequisites, and if they do not return a false, as in there is no loop, then we know that this is not part of the cycle anymore and it's possible. So we add it here, we add it to our order, and then we return true. So yeah, so this does work, as we can see. Okay. So let's go ahead and we'll kind of, all right, let me just do one thing. I'm going to go ahead and copy paste this. And we have course schedule 2 over here. Let's clear this. So it should actually work over here as well. And it's not, what have I done? Oh, sorry. I'm returning true, but actually I have to be returning the order. Yeah, and if it's not possible to finish it, I think we have to return like, okay, they don't have any value, but let's just return like an empty list over here. Okay, see now it works. Yeah, and it works well. So the same thing can be used over here if you just save it to list. Now let's go ahead and kind of do the Kahn's algorithm approach for this. So again, let's store an order because we can use that later. Again, we're going to have an adjacency list. So I can actually probably copy that from over here, whatever we did, to save a bit of time in this from this video. Okay, so we're going to have an adjacency list that's storing course and its prerequisites. And course and prerequisite. No, so in this case, we don't want to do that. So we need to go from a node which has no prerequisites, so our base starting nodes, and then we want to traverse to the nodes that actually require it, because this is where we get our indegree, right? So I want to map the prerequisite to the course that it was required for, because we need to check the indegree. Because if I can finish course 0 and course 1 was dependent on 0 and I have finished 0, then the indegree of 1 now becomes 0. So yeah, we have to map it out differently in this case. And what else was required? We need to have an indegree mapping. So this is going to be 0 into the number of courses. Okay. And then we're going to have a queue. So it's going to become collections.dq, and then v for v and range number of courses if the indegree of v is equal to 0. So I do see that I haven't really mapped out the indegrees over here. Actually, I'm kind of messing things up, but okay. Indegree is here, and one thing we can do for course and prerequisite is just kind of map the indegree while we're doing it. So if this course required this prerequisite, then I know indegree of course is equal to 1. Okay, so this should be correct. And then we can start kind of doing our traversal over here. So while Q course becomes equal to pop left over here, and once I pop it out, I know that it doesn't have any indegree, means it has no prerequisites left. So which also means I can add it to order. So order.append course. And then I want to check the neighbors which are affected by it. So for neighbors in adjacency list of this course, I want to decrement their indegree count. So indegree count of this neighbor is decremented by 1. And now if the indegree has become 0, means it can be completed. I'll go ahead and add it to my queue. So if indegree of neighbor happens to be equal to 0, then we'll do queue.append neighbor. And yeah, so this basically works. And by the end of this, I would have completed everything in the queue. So course schedule 1 asks if all courses can be completed. So in this case, so I could have counted it and been like, this is the number of courses I've completed, like every time I pop something out and say it's possible. But since we're also using this for course order 2 and we're appending it to order, I can just return, I can do return true if the length of order, because it has all the completed courses, is equal to number of courses. Else, if it's not possible, then I just return false. So yeah, I hope I haven't made any mistakes. Okay, this is working fine. All right, this is working fine. So that's good. Let's just copy paste this over here. Kind of comment that out. All right, we add this here, and I don't want to return true, so I want to return order if length of order is equal to number of courses, else return an empty list, because it's not possible. This should work. Okay, and it works fine. Great. So yeah, we have solved 2 problems today, and yeah. So happy coding, everyone. I hope you understood this, and we already discussed the time and space complexity, so yeah.